To have VijayVarma with us. So Vijay got his PhD in Caltech. Don't remember exactly which year, but I think it was 2-3 years ago. Then he was a Klarman Fellow at Cornell in a postdoctoral position, and he recently moved to the Max Planck Institute in Golm or in Berlin with a Marie Curie Fellowship. So Vijay works in many aspects that have to do with the dynamics of binary black holes. In particular, he is behind the waveform model for gravitational waves that most of us consider the state-of-the-art waveform model right now. And he's going to tell us about hints of spin orbit resonances in the binary black hole population. So Vijay, whenever you want to start, please go ahead.
Okay, let me try to hide some of these panels. Okay, thanks Juan for the nice introduction, and hi everyone. So let me jump right in. So with LIGO and Virgo approaching their design sensitivity, we are starting to see tens of binary black hole observations. And this is a movie using numerical relativity simulations for a bunch of these binary black holes. So you can see that they in spiral and merge into a single black hole at the end. So what I want to talk about is how we can take advantage of all the data that we're observing and try to understand where these black holes come from and how they formed and so on. But before going into all of that, let me give a brief outline of what I'll talk about. So the main topic here is about binary black hole spins, including spins in the orbital plane of the binary, and some phenomenon called spin orbit resonances and merger kicks, which I'll explain in more detail. And in particular, I'll talk about how we can measure these orbital plane spin orientations and what we can say about their distribution in nature from the observations by LIGO and Virgo. And finally, some applications for these resonances and kicks. So let me start with some more background. So there, in general, we can think of binary black holes as two classes. One is aligned spin binary black holes, and the other one is precessing binary black holes. And I find it useful to think of these in terms of movies. So in the movies here, you'll see there are two black holes, and there are two arrows on the black holes, which represent the spins of the black holes. And then the arrow in the middle represents the orbital angular momentum, which is always perpendicular to the plane of the orbit. And what is shown here is the... Sorry, is there a question? Okay, so what is shown here is the gravitational wave signal as seen by an observer looking directly into the slide here. So the difference between the movie on the left and the movie on the right is that in the movie on the left, both spins are either along or opposite to the orbital angular momentum, while on the right, the directions of the spins can be tilted with respect to the orbital angular momentum. And you'll see the impact of this once I start the movie. In the movie on the left, the orbital plane is always fixed and the binary just in spirals and merges. While for the movie on the right, the orbital plane wobbles as the binary precesses, and you can see the orbital angular momentum kind of trace a cone around the vertical direction. And this is called precession, and it has a direct imprint on the gravitational wave signal. So on the case on the left, we have a monotonically increasing amplitude and frequency, which is the characteristic chirp signal. While on the case on the right, the orbital plane precession has a direct imprint on the gravitational wave signal, and you can see all of these modulations. Because this precession has a direct imprint on the signal, we can use these modulations to measure the spin orientations of the black holes. You can also, there's a nice analogy you can draw here between binary black holes and tops. So I'm showing some tops from the movie Inception here. So in the case on the left, we have a top which is always rotating about the vertical direction. So its rotation axis remains fixed, while on the case on the right, there's a tilt between the rotation axis and the vertical, and the top precesses. So that's where the name comes from. Okay, so these are the two main classes of binaries that we'll consider. But let me also more formally define the spin parameters here. We have two black holes. Each of them has an associated spin vector, which is a 3 vector. And it's convenient to think of the spins in a frame which is attached to the binary. So the z-axis in this frame is defined to be the direction of the orbital angular momentum at some point in the binary evolution. And the x-axis is the line of separation between the two black holes at the same time. And then we can decompose the spins in spherical coordinates, and you can think of the spins as parameterized by two spin magnitudes, chi1 and chi2, two tilts with respect to the orbital angular momentum direction, and then two azimuthal angles, phi1 and phi2, which are defined with respect to the line of separation. These are dimensionless spins, which you can think of as the spin angular momentum of each black hole divided by mass squared of that black hole. So the value goes from 0 to 1, where 1 is an extremal spin. Okay, so and in addition to these two phi1 and phi2 angles, it's usually convenient to think of the difference between phi1 and phi2, which we'll call delta phi, which tells us the difference between the orbital plane spin orientations. And so the reason we care about all of these spin angles is that they have important implications for two phenomena called spin orbit resonances and merger cakes, which I'll talk about in the next slide. But let me briefly motivate the reason for this project is we want to measure these angles and see what they can tell us about these astrophysical phenomena. And also about the distribution of these angles in nature will tell us something about these phenomena as well. So that will be the main focus of this talk. Okay, so why do we care about these angles? There are two important phenomena in which these angles become very important. The first is binary black hole merger cakes. So as the binary evolves, it radiates these gravitational waves, which carry away energy and angular momentum, and this causes the binary orbit to shrink. But at the same time, the gravitational waves can also carry away linear momentum from the system, which effectively imparts a kick velocity or a recoil to the final black hole that is left behind. So I'll show an example here. You'll see that after the black holes merge, the final black hole runs away with a high velocity, but I'll speed up the movie to make that more clear. There you go. So in this particular case, the kick velocity is pretty high. It's about 100th the speed of light. And the largest kicks can get up to thousands of kilometers. The largest value, I think, is 5,000 kilometers per second. And these high kick velocities are actually larger than the escape velocities of most known galaxies. So what this means is that this final black hole can get ejected from the galaxy after the merger. And this has important implications for understanding how heavy stellar mass black holes form, because one proposed formation mechanism is that these heavy black holes form through repeated mergers of binary black holes. But if the kick velocity is large enough, after the first merger, the final black hole will just get ejected and it would not participate in the second merger. So understanding these kicks is important for understanding how black holes form, how heavy black holes form. The other astrophysical phenomenon where I should mention that these kick velocities depend very sensitively on the orbital plane spin angles. So measuring those angles will allow us to measure the kick velocity. The other astrophysical phenomenon where these angles become very important is spin orbit resonances. And these are not really resonances, but it's a name that has stuck. So we will go with that. But you can think of them as equilibrium configurations which act as attractors for binary black holes. And there are two particular resonance modes where the three angular momenta here, the two spin angular momenta and the orbital angular momentum, they become locked into a fixed plane, as you see here. And as the binary precesses, the three vectors precess at the same frequency while maintaining that planar configuration. And there are two modes of these resonances. The one I've shown here, where the two spin directions are kind of anti-parallel. And so that in that case, you get a delta phi of plus or minus pi. The other case is where delta phi is 0, where both are on the same side. So these are two equilibrium configurations, which are called spin orbit resonances. And the reason these are important is that when you have certain conditions, such as high supernova kicks and stellar tides, and I'll talk about these in my next slide, when you have these kind of conditions, binary black holes can be driven towards these resonances. And we should, if these resonances are important, we should find a preference for delta phi to be plus or minus pi or 0 when we observe the binary black hole. And
Vijay, can I ask a question?
Yes, go ahead.
So I think you just answered it, but you're meaning that these two locked configurations should be preferred in nature. It's not that any given binary started at any given value of this delta phi will end up in plus minus pi.
No, on a population level, on average, this should be preferred, not for a single event.
Okay, thanks.
Yes, so if we do observe these kind of preferences, then that will tell us something about supernova kicks and stellar tides, so we can use binary black holes to learn about these phenomena. Okay, so that's the motivation here, the reason why we want to measure these angles. But let me talk a little bit more about under what conditions these spin orbit resonances can occur. But first, I should talk about the main formation channels for binary black holes. And there are generally two main formation channels that are considered. One is dynamical encounters in dense stellar environments like globular clusters, where you can have random encounters between black holes. So this is a movie which is based on a simulation of these clusters. And you can see that there are a bunch of black holes and stars flying by, and sometimes they have random encounters, and they can get captured in a bound orbit and eventually merge. So that's one formation mechanism. The other one is that you start with an isolated stellar binary, and here is an example from Star Wars, and you have two stars that are orbiting each other. And eventually, both of these stars will go supernova and form a binary black hole, and that will also merge. The reason this is a separate formation mechanism, which is considered as a separate formation mechanism, is because in this case, because these stars are together for a long time, the stellar tides between the stars tend to align the spins of the two stars, which will result in the two black holes having aligned spins. While on the case on the left, because these are random encounters, there shouldn't really be any preference for the spin directions, and we should expect that the spin directions will be isotropically distributed. So these are roughly the two main formation mechanisms that people generally consider. And we can think about whether spin orbit resonances are possible here. So right off the bat, we can show with post-Newtonian spin evolution that if you start with an isotropic spin distribution, you should get an isotropic spin distribution at merger. So if you start with a binary that is widely separated and a population of isotropic spins, then that isotropy is preserved by the time you get to the LIGO frequency. So this means that dense stellar environments should not be a host for these spin orbit resonances. In general, there should not be a preference for any delta phi. On the other hand, there are certain conditions under which this can happen. In particular, if the initial tilt of the binaries, initial tilts of the binary, which is the tilt angles at wide separation, if the tilt of the larger the heavier black hole is less than the tilt of the secondary black hole, then you can show with post-Newtonian evolution that the delta phi 0 mode is preferred at 20 hertz, which is where the LIGO detector starts to observe these black holes. And similarly, if the initial tilt of the heavier black hole is larger, you get the other resonant mode, where you should find that there's a preference for delta phi is pi. So that's kind of shown here in this paper, where if you start with initially less tilts for the primary, you get a preference. So this here, the blue curve is the distribution of delta phi at wide separation at very low frequency. And then the black curve is this distribution at 20 hertz where LIGO will observe it. So you can see that even though you start with a flat distribution, by the time you get to late in spiral, or when you're observable by LIGO, you'll have a preference for delta phi to be 0 in this case, and in the other case, you'll have plus or minus pi. So this gives us one way to form the get these spin orbit resonances and these delta phi preferences. But then the question is, how do we get these kind of initial conditions? So it turns out that there are some conditions under which this is possible.
Vijay, Tom has a question.
Yes, go ahead.
Well, and the blue initial condition seems like it comes from isotropy. So
that's right.
Well, okay, but you have a bullet point on this slide that says isotropy is preserved. Right.
So it comes from isotropy, I guess, in the delta phi direction, but not in the tilt directions. So, the tilt, this is not isotropic as such. It's only uniform in the delta phi, but the tilts are not isotropic.
So okay, phi one means the tilt of the heavier black hole.
That's right. Yes.
Okay, but I mean, it's always going to be the case that either phi one is less than or bigger than phi two.
Right. So this is not for an individual binary black hole, but on a population level. So if on average there's a preference for smaller tilts for the primary black hole, then you'll get this.
Okay, so then somehow these are like models of populations which are not isotropic.
That's right.
Not that you took an isotropic population and then sliced it up into two parts. Well, again, if you take an isotropic population and just separate it into two parts with phi one less than or greater than phi two, then I guess you don't get anything.
That's right. Although it depends on how strong this preference is. So if you make this a very mild preference, then this peak would be very mild also. So at some level, you can do exactly what you're saying, and you'll get two very mild peaks here, and you add both of them, and you get a flat distribution.
Yeah. Okay. That's much clearer. Thanks.
Okay, so this gives us one mechanism under which this spin orbit resonance can happen, but we still need to find a scenario where these kind of initial conditions are possible. And it turns out that there are some scenarios in isolated binaries where this is possible. But first, let me talk about the standard scenario. So we have two stars, one is heavier than the other. And because of the tidal interactions, the spins of the two stars tend to align along the orbital angular momentum. And eventually, both of them will go supernova, and you'll get an aligned spin binary black hole. So there are a lot of details that I'm skipping here, but those are not particularly important for the topic of this talk, such as common envelope evolution and so on. But this picture of aligned spin binaries gets more complicated when you consider supernova kicks. So these kicks are different than the merger kicks that I talked about before, but the idea is very similar. The supernova mechanism can also radiate linear momentum in anisotropic directions, which means that when the supernova happens, the black hole can be imparted with a recoil or a kick. And to be clear, I'll always refer to the kicks at supernova or kicks at formation of the black holes as supernova kicks, and the merger kicks as regular kicks. Okay, so when the in the simple scenario, we assume that this supernova kick is small enough that the binary continues to be an aligned spin binary. But if the kick is large enough, essentially what this does is it displaces this black hole while keeping the other star kind of at the same state, and you get a different orbit now. So this black hole has moved up, so you get a different orbit. But in the simple supernova kick scenario, the spin of the black hole remains along the same direction. And we can consider more complicated scenarios as well, but I'll stick to the simple one here. So at the end of the day, what we have is a new orbit, but because the spin directions are same, but the orbital angular momentum direction is now different, you now have a precessing binary. And but at this stage, we have one black hole and the other one is still a star. And now there's a long evolution before this star is also ready to explode. So the heavier star explodes first because it consumes its fuel faster. And then over a longer evolution, as the binary orbit also shrinks, and this happens because of the common envelope and binary hardening and so on, but we can skip those details. And essentially, you'll get a more tightly bound binary. And at the same time, because of the stellar interaction, because of the tidal interactions of the star, because of tidal effects in the star, the star tends to align itself along the orbital angular momentum. But this doesn't really affect the black hole because it doesn't have the stellar tides. So what you have at the end of this long evolution is the black hole spin is still misaligned, but the spin of the secondary star is aligned along the new orbital angular momentum direction. Okay, now eventually this star will also explode, and this will also get a supernova kick. But because the orbit is now more tightly bound, it's harder to displace the black hole, and the effect of the supernova kick on the orbit is slightly smaller. But you can still get a new tilt. So that's what I represented between this orbit and this orbit. There's a new tilt of the orbit. And now you have this binary black hole where both black holes have tilted spins with respect to the orbital angular momentum. And I'll rotate the binary to make it a little more clear. Okay, so at the end of the day, because of this complicated interaction of the stellar tides, what happens is because we are aligning the secondary black hole in between the two supernova, and because the secondary supernova is generally less effective in tilting the orbital plane, generally we should have a larger tilt on the heavier black hole and a smaller tilt on the smaller black hole. So again, this is not necessarily true for each individual binary black hole, but we should expect this on the population level if the supernova kicks are large enough and if the stellar tides are large enough. So if those conditions are met, we should generally expect that the tilts of the heavier black hole are larger than the tilts of the lighter black hole. And this, as I showed before, should prefer the delta phi pi mode. And there is some other complication that can happen where in between these two stages, before the star explodes, it also, when it finishes consuming its fuel, it generally expands and transfers some of its mass to the secondary star. And if this mass transfer is very efficient, there are scenarios where the heavier black hole ends up becoming the lighter black hole. So this is called a the heavier star ends up becoming the lighter black hole. And this is called a mass ratio reversal. And what you end up with is that this ends up being the smaller black hole, and this will be the heavier black hole. And in that case, you'll find that the tilt of the heavier black hole is smaller, and this can be a way to get the other spin orbit resonance mode, the delta phi is 0 mode. So overall, this supernova kicks and stellar tides combined with the post-Newtonian evolution gives us a formation mechanism for these spin orbit resonances to lead to these preferences in the delta phi angles. But before I go to the next part, let me see if there are any questions.
Not so far.
Okay, great. Okay, so now that we have this mechanism for formation of these resonances, we can try to ask the question, can LIGO observe these resonances? And so we have to ask, how well can we measure these angles phi 1, phi 2, and delta phi, and also what we can say about their distribution in nature. There's one problem right away. These angles are known to be very hard to measure with LIGO. In general, the best measured spin is a linear combination of the spins called the effective spin, and the individual spin parameters are not very well measured. So conventional wisdom tells us that we really need next generation gravitational wave detectors, which will appear possibly in the 2030s. However, as I'll show, this is a bit of a lie. We can actually do something with LIGO and make some useful measurements already, or with LIGO at design sensitivity. So I'll talk about that in the next part of my talk. Okay, so, but before that, let me give some background on how spins are actually measured. We essentially use Bayes' theorem, where we have we want to estimate the probability, posterior probability of some parameter, and that's given as the product of the likelihood of observing some gravitational wave data given those binary parameters and some prior assumption for those binary parameters. And we can compute this likelihood under the assumption of Gaussian noise. And you can compute it as this exponential, where there's an inner product where you take the difference between the data and some waveform model. And so this is essentially the noise, and we're making the Gaussian noise assumption here. And this with this likelihood, we can define our posterior distribution like this, and we can use a stochastic sampling algorithm like MCMC or nested sampling to draw samples from these posteriors. But the complication here is that the spins evolve as a function of time. So you have to specify at what point in the evolution you will measure the spins. And the typical choice made by LIGO and Virgo is that the spins are specified at 20 Hertz, which means that we measure the spins at the point where the gravitational wave signal reaches 20 Hertz. And this is for total masses like 60. This happens around 10 orbits before merger, roughly something like that. So it's somewhere in the inspiral, typically. And this is an example of spin measurements, but I'm just showing some commonly measured spin parameters just to give an example of a spin posterior distribution. Okay, so essentially what is done is you have a waveform model, and then you vary the waveform parameters, and you get, by using the Bayes theorem, and you get a posterior distribution. But some more details about these, about the parameter estimation setup. We use a package called Parallel Bilby, and for the waveform prediction, we use the numerical relativity surrogate model called NR-SIR70Q4. And what this model does is it takes hundreds of numerical relativity simulations, and it uses data-driven methods to interpolate between those simulations. And at the end of the day, it produces a very accurate model that reproduces the precession effects in the numerical relativity simulations. And this is very important to be able to capture the orbital plane spin angles from gravitational wave observations. Okay, so that's the setup for the parameter estimation. And as I mentioned, spins are typically measured at 20 Hertz, gravitational wave frequency of 20 Hertz. Instead, in this work, what we propose is measuring the spins at a point very close to the merger. And the reason is that we find that the waveform is more sensitive to these orbital plane spin angles near the merger. So I'll explain what I mean by that in later slides. But first, let me talk about how you can measure the spins near the merger. So the standard choice is to measure the spins at 20 Hertz. But if you want to always measure the spins near the merger, one simple way to do this is to measure it at the ISCO frequency, which is the innermost stable circular orbit. And it's defined in this dimensionless manner. And this always happens around 2 orbits before merger. And it's also generally taken to be the point where post-Newtonian evolution breaks down and you need numerical relativity. So you can define a point in the evolution like this ISCO frequency, which always happens near the merger, independent of binary parameters. And so that lets you, if you always measure the spins there, you'll always be near the merger. And you should notice that this is this dimensionless quantity F times M. And the reason is that because GR is scale invariant, you can always remove the scale through by rescaling the total mass. And all length and time scales are proportional to the total mass, which means that the frequency scales are inversely proportional to the total mass. And so m times f ref is always a dimensionless quantity. Something similar you can do. Instead of thinking in terms of frequency, you can also think in terms of time before the merger. And once again, because time is proportional to the total mass, you can define it in this dimensionless type time and always measure the spins minus 100 m before the peak of the gravitational wave signal. And this also happens roughly 2 orbits before merger. So this gives you a different way to always measure the spins near the merger. So why is this useful? So this is an example of the spin measurements you would get by measuring near the merger. So what I'm showing here is the posterior distribution of phi1, phi2, and delta phi, the difference between them. And let me first just focus on the 1D distributions here. The blue curves are the spins as measured at 20 Hertz, which is the standard choice. And the purple curve is at minus 100 m, and the green is at ISCO frequency. But looking at phi1 and phi2, you'll see that the blue curve, which is at 20 Hertz, is generally quite flat, and there's not a lot of features there. However, when spins are measured at minus 100 m, there are much more prominent peaks in the posterior. And we are getting a much better understanding of what the spin is at that reference point. One thing to point out is that the location of the peak is different between ISCO and minus 100 m. And the reason is that these phi1 and phi2 evolve on an orbital timescale. So if you remember, these are defined with respect to the line of separation between the two black holes, which evolves on the orbital timescale. So these also evolve on the orbital timescale. But these are both roughly equally good points to measure these angles. And the other thing to note is that there's no significant improvement in the delta phi distribution here. And also the peaks are at the same point. And the reason is that delta phi, unlike phi1 and phi2, doesn't evolve on the orbital timescale. It evolves on the longer precession timescale, which happens over many orbits. Okay, so the overall point here is that we're getting much better measurements of phi1 and phi2, but not for delta phi for this event. But I'll show later on with some numerical relativity injections that delta phi will also improve near the merger at higher SNR. So essentially what this is showing is that if you measure the spins near the merger, you'll get sharper peaks in your posterior. One important thing here is that there's no new information gained here by measuring the spins near the merger. We are still using the same waveform model, and we're still fitting it to the same observations. And in fact, if you take the spin measurements at 20 Hertz and evolve them forward in time to minus 100 m, you'll get something very, very similar to measuring the spins directly at minus 100 m. So this means that this can be done entirely in post-processing as well. So, however, even though all of this spin information is already there at 20 Hertz, as I'll show later, the waveform is more sensitive to these angles near the merger, which lets us measure them better. But I'll explain why this doesn't work at 20 Hertz in a few slides. But for now, the takeaway is that just by going close to the merger, you get sharper posteriors in phi1 and phi2. Okay, so this is showing the same thing, but now here I'm showing the spin directions in the orbital plane. So this is the X and the Y direction. This is the lighter black hole. This is the heavier black hole. And each point here corresponds to a posterior sample. So the density of the posterior distribution is kind of shown by the density of the points here. And initially, I'm showing the spins as measured at minus 4300 m, which is the earliest time for the surrogate model. And then as I start the movie, you'll see the spins as measured at different times, and you should be able to see this improvement in the spin direction measurement. Okay, so as we get close to merger, you'll start to see more features. You can see there's this clumping in the posterior. Okay, so this is again now at -100 M. So initially it looked quite isotropic, but now there is this stronger preference in this direction. This is essentially what I was showing in the previous plot, but shown as a function of time. And the reason this is rotating so quickly is again because these are defined in the orbital in a plane which is attached to the line of separation. So the rotation you're seeing is the orbital rotation. So it's just a frame that is attached to the black holes. It kind of looks like a washing machine because of that. Okay, so maybe I should say that you might jump the gun here and notice that phi1 and phi2 have opposite directions. So this might look like spin orbit resonances, but that is a red herring. If you see this plot, there's really no strong preference in delta phi. In fact, even though phi1 and phi2 are separated by roughly pi, delta phi actually prefers 0. And what this is telling us is that we're not really measuring phi1 and phi2 at the same time. We're only measuring one of them. As a result, delta phi is not as well measured. So in general, phi1 and phi2 are better measured on their own, but at current sensitivity, we're not measuring delta phi very well, whether you're at 20 Hertz or -100. Okay, then there are a few more examples like this. So that was just one event. And now these are a bunch, 12 other events that we consider. And you can see what I'm showing here in the solid lines are the spin measurements at -100 M, and the dashed lines are spin measurements at 20 Hertz. And you can see that in general, the solid lines are more sharply peaked than the dashed lines. So this feature is seen in a lot of events. So I'll skip some slides here. But we can ask, why is it really better to measure the spins near the merger? But first, let me show an example of what happens to the spins as you get closer to the merger. So these are two events, and the lighter colors show the spins very early in the spiral at -4000 M. And then the darker, as you get towards the darker colors, you're getting towards -100 M. And you can see that there is kind of a systematic improvement in how sharp these posteriors are. And so as we get closer to the merger, we seem to be improving our spin, the peaks here. To understand this, you can look to the Fisher matrix, which essentially gives us an estimate of the uncertainty in a measurement of any parameter. So it's defined as this inner product between the derivatives of the waveform with respect to various parameters. One thing to note here is that the Fisher matrix method is only applicable in the high SNR limit, but in our case, we mainly consider it as a proxy for how sensitive the waveform is to these parameters. So because you're taking the derivatives here, and when computing the variance between the parameters, you take the inverse. So this means that if the waveform is more sensitive, you have stronger derivatives, and when you take the inverse, you get lesser variance. So in general, smaller errors in the Fisher matrix method imply more sensitive waveform to the parameters. So again, as we get towards the darker colors, I'm showing here the statistical uncertainty or this variance, square root of that in phi1 and phi2, and you can see that as you get closer to the merger, in general, these errors become smaller, which indicates that the waveform is more sensitive to these parameters, which explains why the spins posteriors become sharper. So this essentially tells us that measuring spins close to the merger is a good place to measure these orbital plane spin orientations. But as I mentioned earlier, all of this information is already there in the spin posterior at 20 Hertz. It's just that by the time, as you can think of it as evolving backwards in time from -100 to -4000. And as you evolve it backward in time, there are a lot of orbital cycles and also sometimes precession cycles. And this kind of spreads this information in the 6-dimensional spin posterior. But if you look at it very close to the merger, the information is very nicely packed into the phi1 and phi2 posteriors, which make it a nice point to measure these spin angles. Okay, one other thing I mentioned is that the delta phi distribution was not improving as we get close to the merger. So we also tried some numerical relativity injections. And you can see here the red posteriors are the spin posteriors at -100 m, and the blue posteriors are posteriors at 20 hertz. And you can see that in general, there's an improvement as you get close to the merger, also in delta phi. So we expect that as we get louder signals, all of these angles will be better measured near the merger. Okay, so let me quickly talk about the final part of my talk, which is now that we have all of these improved measurements, what can we say about their distribution in nature? So we have 31 events from the latest gravitational wave catalog from LIGO-Virgo. One note is that these are all events with total mass greater than 60, because the surrogate model only has 20 orbits, which means that it doesn't apply to the low mass signals, which will be seen by LIGO with more than 20 orbits. So as I showed before, we have several events with improved constraints on phi1 and phi2, but not delta phi. Then the question is, can we say something about the distribution of these angles in nature? The approach we take is standard hierarchical analysis, and we assume that the true spin of each event is drawn from some unknown distribution, and we want to try and constrain the properties of that distribution. So these are some technical details for the experts in the audience, but I'll skip those in interest of time. And so we essentially want to constrain the population of the full spin degrees of freedom, which is the chi1, chi2, the tilt angles, and the orbital plane spin angles. So we'll only consider phi1 and delta phi because phi2 is redundant given these two, and we are more interested in delta phi because of the spin orbit resonances. And our underlying assumption for this spin population is that it is given by some formula of some combination of posterior distributions in these parameters, and we want to measure the parameters of those distributions. So we assume that it's given by some spin distribution with some unknown hyperparameters that we want to measure. Again, for the experts in the audience, we model the spin tilts and spin magnitudes following the default spin model in the LIGO population paper, but I'll skip those details here. For the purpose of this talk, you can just think of it as modeling the orbital plane spin degrees of freedom independently of the other ones. So we assume that the underlying spin distribution is given by some product of posterior distributions, and we make the simplifying assumption that the underlying spin distribution for phi1 and phi2 follows a Gaussian type distribution. The particular distribution is called von Mises, and this is like a Gaussian distribution, but with periodic boundary conditions. So you can see that it looks like a Gaussian, but whenever there is this boundary where you have periodic boundary condition, it wraps around and continues. And this is a simple assumption you can make for phase parameters like phi1 and delta phi. So given this assumption, we want to measure the hyperparameters, which are the means and the standard deviations of these Gaussian-like distributions. And once again, we follow hierarchical inference where we combine all of these events, and we can define a likelihood, which I won't explain in detail, but you can think of it as a product of the contribution from each of the events because each event is independent. And again, we use Bayes' theorem where we write a posterior distribution for our hyperparameters given our set of observations, and we have this likelihood, and we have some prior assumptions about the hyperparameters. And again, we use a sampling algorithm to draw posteriors for these hyperparameters, which are these mu and sigma parameters. So I'll jump right into the results. So here I'm showing the posterior distribution for the mean and the standard deviation for the phi1 and delta phi distributions. And we make two prior choices here. One, first for the mean parameters, we always assume that it is uniform in between minus pi and pi, and the priors are shown as dashed lines in these in the diagonal plots here. But for the sigma parameters, we consider two prior choices. One is a Jeffreys prior, which is log uniform in sigma, and it's a commonly used prior for scale parameters like sigma. And the other choice is just flat in sigma. The solid curves here show the posterior distribution, and immediately you can see that the posterior for the width parameters, sigma 1 and sigma 2, is entirely dominated by the prior. So we're not really measuring the width of the distribution here. On the other hand, the posterior for the mean parameters seem to have some information gain, especially for the Jeffreys prior, which prefers smaller widths. We see a stronger preference for some values of delta for mu. In particular, there's a preference for mu to be around plus or minus pi, and for delta phi to be plus or minus pi, and for phi 1 to be around minus pi by 2. To get a better idea of what this implies, you can look at the effective population distribution that we get from this. And to do that, essentially, we take posterior samples from these plots and we plug into this von Mises distribution. And each posterior sample gives us one curve, one posterior distribution. And here I'm showing the 90% width on several such distributions that are generated from this posterior. Essentially, the key takeaway is that for the Jeffreys prior and for the flat prior, these preferences in mu translate to preferences in the distribution of the population. And you can see that for delta phi, there seems to be a preference for plus or minus pi, while for phi 1, there's a preference near minus pi by 4, something like that. But the important thing is, because the widths are not very well measured, the prior has a big impact on how much we can say about whether the real distribution is like this or not.
Vijay, two questions if I can.
Sure.
So if I saw correctly in your previous slide, the prior you're using for the distribution in the population of these in-plane spins is this von Mises prior. Mm-hmm. Basically picking sort of at pi and minus pi. So could your inferences be driven by this prior?
No, so this prior, we as long as we use a wide enough prior for the width, we also allow a perfectly flat distribution in our model. So we allow the delta phi to be up to 4 pi, in which case the distribution would look perfectly flat.
Okay. And can you remind me what the Jeffreys prior is? If I recall correctly, it's a prior that basically follows the likelihood, but I don't quite remember it.
It's just a log, uniform in log sigma prior.
Okay.
So it's supposed to be this minimally informative or uninformative prior, something like that.
Okay, thanks.
Okay, so let me try to wrap up. So in the spin population, we find that there may be a preference for delta phi to be plus or minus pi, which could point to spin orbit resonances. And this is interesting because maybe we're getting close enough to understanding how prevalent these spin orbit resonances are, and which would tell us something about supernova kicks and stellar tides. The other thing is that we find this peak in the phi 1 population, which is not really predicted by any astrophysical predictions. But the thing here is that the location of the phi 1 peak is not particularly important, but the fact that it peaks at all is unexplained, and this is something we want to look into. Okay, and finally, this implies, this suggests that spin orbit resonances could be playing a role, but this should be taken with some grains of salt, because we don't really measure the widths of the phi 1 and delta phi 1 and delta phi distributions, and both populations are still consistent with the flat distributions. and I'll skip the other details here. And for the experts, I want to show that we also have a constraint on the kick population, which I'll skip so that I can take some questions and go directly to summary. The constraining the full spin distribution of binary black holes is important for these phenomenon called spin orbit resonances and kicks. And generally, the LIGO-Virgo papers measure the spins at 20 Hertz, but we find that measuring the spins near the merger, for example, at -100 m, leads to better constraints on the orbital plane spin angles. And using these constraints, we analyze 31 binary black hole events to constrain the astrophysical distribution of phi1 and delta phi. And in general, we find that there can be a preference of delta phi to be plus or minus pi, which is a predicted signature of spin orbit resonances. But because we are unable to measure the widths of these distributions, we need more observations to confirm this. There's also an unexplained peak in the phi1 population, which would be interesting to follow up and understand. And finally, we have some constraints on the kick population and retention rate for merger remnants. For example, our kick population suggests that globular clusters are not a likely site for second generation mergers. But again, that's something for the experts. So I'll end here and take any questions. Thank you.